So good afternoon, everyone. I'll be taking this class of chemical process technology live session for the week 4, and I will start in 5 minutes. Hello, am I audible to you? Okay, we'll start in 5 minutes. So okay, now I'm going to start. I hope the screen is visible to all of you. So let's start this session. The first question is what is the second most manufactured chemical? What is the second most manufactured chemical in the world? What is the second most manufactured chemical after sulfuric acid in the world? So I'll give you 1 minute. You try to answer, then I will tell the answer. So here the answer is ammonia. The most manufactured chemical is sulfuric acid and next is the ammonia. So here the answer will be ammonia. Next question is what are the natural fertilizers? What are the natural fertilizers? What are the example of natural fertilizers? So the answer will be saltpeter, which in the form of KNO3, potassium nitrate, chili saltpeter that is sodium nitrate, and guano that is the seabird droppings. These are the natural fertilizers. However, the industrial manufactured fertilizers are ammonia based fertilizers like urea, ammonium phosphate, ammonium nitrate, etc. So here I have asked about the natural fertilizers. So saltpeter, chili saltpeter and guano will be the answer. Next is the Russia is the top producer of ammonia in the world. Russia is the top producer of ammonia in the world. Is it true or false? Russia is the top producer of ammonia. Is it true or false? So here the answer will be false. Okay, because Russia is not the top producer. So if you connect it to the lecture, you can see here that the top producer is the China. 32.6% of ammonia is produced in China. Then comes the Russia. Okay. So Russia is the second top producer, not the top producer. So here the answer will be false. Next question is, what is the amount of ammonia production in India? What is the amount of ammonia production in India? You can go to the same slide and see the answer. So you should tell this answer. So here the answer will be 7.6%. Okay, you can go to the slide and see that India's production is of 7.6%. Next question is what is the production rate of modern ammonia plant? What is the production rate of modern ammonia plant? What is the production rate of modern ammonia plant? So here the answer will be 750,000 metric ton per year. The production rate of modern ammonia plant is 750,000 metric ton per year. Next question is what are the solid fertilizers produced from ammonia? What are the solid fertilizers produced from ammonia? What are the solid fertilizers produced from ammonia? So here the answer will be urea, ammonium nitrate, ammonium sulfate and ammonium phosphate. These are the solid fertilizers produced from ammonia. Next question is the what chemical is produced after the partial oxidation of ammonia? What chemical is produced after the partial oxidation of ammonia? What chemical is produced after partial oxidation of ammonia? So here the answer will be HCN, not HNO3. Okay, because I am showing you this is ammonia. After full oxidation of ammonia, nitric acid HNO3 is produced. But after partial oxidation of ammonia, hydrogen cyanide, that is HCN, is produced. So in this case, our answer will be HCN. Next question is ammonia reacting with methanol produces tertiary amine. Ammonia reacting with methanol produces tertiary amine. Is it true or false? So ammonia reacting with methanol produces tertiary amine or not? So let's see what happens in this reaction. That is ammonia reacting with ethanol produces primary amine. Okay, then secondary amine, that is okay, this is secondary amine, and third one is the tertiary amine. So the structure of tertiary amine is like this. Here this is CH3, here CH3, and here CH3. So ammonia reacting with methanol produces all type of methylamines. So tertiary amine is also produce tertiary amine. That means the sentence is true. Okay. Next is the nitrogen has exceptionally high electron affinity. Nitrogen has the exceptionally high electron affinity. Is it true or false? So here the answer will be true. Nitrogen has extremely high electron affinity. Next question is the what is the surrounding condition maintained for production of ammonia? What is the surrounding condition maintained for the production of ammonia? So here the question is, what is the surrounding condition maintained for production of ammonia? So here the answer will be high pressure and temperature, low temperature. Okay, high pressure and low temperature is needed for the ammonia production. So high pressure means that pressure should be maintained at 100 to 250 bar, and the temperature range is in between more than 670 Kelvin. Okay, more than 670 K. Next question is the, what is the maximum percentage of ammonia production in ICI quench reactor? What is the maximum percentage of ammonia production in ICI quench reactor? What is the maximum percentage of ammonia production in ICI quench reactor? Here the answer will be 20%. Only the 20% of ammonia can be produced by this kind of quench reactor. Okay, so next question is, the equilibrium curve is governed by kinetics. Is this true or false? So in any kind of synthesis, there are two kind of curves, equilibrium curve and the maximum rate curve. So equilibrium curve is governed by kinetics or thermodynamics. Based on that, you can say is it true or false. So here the answer is not true. That means it is false. Equilibrium curve is governed by thermodynamics, not kinetics. Okay, rather maximum rate curve is governed by kinetics. Kinetics means how speed a reaction happens. Okay, so that is what tell about the speed of the reaction. That is why maximum rate curve is governed by kinetics. Okay, so here it is false. Next is the in Kellogg quench reactor, feed is delivered from the bottom. In vertical Kellogg quench reactor, feed is delivered from the bottom. Is it true or false? So here the answer is true, because if you remember the diagram of the quench reactor, Kellogg's quench reactor, I'm showing. So this is the Kellogg's quench reactor diagram. So you can see that feed is supplied from the bottom and product is collected. It goes up with this, and then it enters the catalyst beds, 4 catalyst beds, and through quench gas it is cooled down, and and then the product is emerged out from the top portion. So here the answer will be true. Next question is, in Kellogg's quench reactor, continuous catalyst bed is used or not? In Kellogg's quench reactor, continuous catalyst bed is used or not? So here the answer is false. So in Kellogg's, as you have seen just that here 4 different catalyst beds are used. So they are not continuous. So here the answer will be false. Next, what are the advantages of using axial Kellogg quench reactor for production of ammonia? What are the advantages of using axial Kellogg quench reactor for production of ammonia? What are the advantages of using axial Kellogg quench reactor for production of ammonia? What are the advantages of using axial Kellogg quench reactor for production of ammonia? So here the answer will be larger catalytic area per unit volume, low pressure drop, smaller catalyst size, higher production rate, and cross flow pattern. If I show you the diagram, then that will be more clear. So here you can see that catalyst sizes, catalyst size of the catalyst are low here, so that is why it gives larger surface to volume ratio. Then this leads to the low pressure drop also, that is why the pressure is easy to control inside the axial Kellogg quench reactor. Then there is a cross flow pattern. So here the feed is coming, then quench gas is going from here, and this catalyst and in the catalyst based reactions also are happening. So this is creating some kind of cross flow pattern inside the reactor, and product is going out from here. So that's cross flow pattern helps in good mixing also. So that is why these are the advantages of Kellogg's quench reactor in actual position. Next question is the what is the name of commercial ammonia synthesis reactor? What is the name of commercial ammonia synthesis reactor? What is the name of the commercial ammonia synthesis reactor? So the name is Haldor-Topsoe reactor. It is the name of the commercial ammonia synthesis reactor. Next question is the in radial flow reactor, two annular catalyst beds are used. So you know that Haldor-Topsoe reactor is a kind of radial flow reactor. So where two annular catalyst beds are used or not? Is it true or false? So here the answer will be true. In radial kind of flow reactor, radial type flow reactor, two annular catalyst beds are used. Okay, so next is the which reactors use indirect cooling method? Which reactors use indirect cooling methods? The answer will be Kellogg horizontal reactor and the Haldor Topsoe reactor. These are these reactors use indirect cooling method. Indirect cooling method means that the heat exchangers are used between the catalyst beds. You know that in the catalyst beds reactions are happening of ammonia synthesis. So ammonia synthesis is an exothermic reaction, so it produces heat. So too much heat is also bad for the reaction to continue, for the production, right? So that is why at every stage at the catalyst bed stage the reaction is happening, then they use a heat exchanger where heat is reduced of the product, where it is reduced, then again that there is catalyst bed where the reaction is happening, and that is why it is like repeatedly it is heated and they again cooled to process the whole ammonia synthesis. So that is why these beds use repeated stages of heat exchanger and catalyst bed to control the overall temperature of the ammonia. That is why it is called the indirect cooling method. Next question is the what is the conversion of single pass synthesis in ammonia production? What is the conversion of single pass synthesis in ammonia production? What is the conversion of single pass synthesis in ammonia production? The answer is 20 to 30%. Okay. In single pass synthesis, the ammonia production is 20 to 30%. Next is the ammonia is recovered before recycle compression at lower pressure. Is it true or false? Ammonia is recovered before recycle compression at lower pressure. When ammonia is recovered before recycle compression, it is recovered at lower pressure or higher pressure. So based on that, I have asked the question, is it true or false? Due to technical glitch, the share has been stopped. So now I have again shared it. I hope it is visible. So the question was, ammonia is recovered before recycle compression at lower pressure. Is it true or false? So here the answer is true. When ammonia is you can see the chart. Um, so here you can see that ammonia is recovered before Recycle compression. In this diagram, you can see that ammonia is condensed at lower pressure. Okay. Ammonia is condensed at lower pressure, resulting in higher ammonia concentration in the gas. Okay, so here the ammonia concentration will be higher if we keep lower pressure. So here the answer will be true. Next question is, the ammonia is condensed at lower pressure with lower ammonia concentration. So I have already just told the answer, so you should answer this. Ammonia is condensed at lower pressure with lower concentration of ammonia. Is it true or false? So it is quite obvious that the answer will be false. Okay. Next question is, the why two stages of product condensation are required? Why two stages of product condensation are required in case of ammonia production? Why two stages of product condensation are required? So the answer will be to avoid the compression of liquid ammonia. So if we compress the liquid ammonia, that will not be helpful for our production, right? So that is why we are avoiding the compression of liquid ammonia. That is why we use two stages of product condensation. Next is, the what is the process of elimination of CO2 called? What is the process of elimination of CO2 called? So while producing ammonia, there might be some impurities, that is carbon dioxide too. We have to eliminate the carbon dioxide to get the pure ammonia. So what is this process called? What is the process of elimination of CO2 called? So here the answer will be methanation. Okay. So the answer will be methanation. Next question is the carbon oxides are highly poisonous to ammonia synthesis catalysts. Carbon oxides are highly poisonous to ammonia synthesis catalysts. Is it true or false? So the answer will be true. Carbon dioxides are detrimental to the ammonia synthesis process. That is why they are removed by the methanation process. Okay, so it is true here. Next question is in reformer, reactants react with what type of elements? In reformer, reactants react with what type of element? Means suppose there is a reactant, any kind of reactant. So if we say that reforming reaction is happening of that particular reactant, so what does that mean? So that is what I have asked. So the answer would be steam and oxygen. When something is reacted with steam and oxygen, we call it reforming reaction. Okay, so there this is the multiple select options. So this will be steam and oxygen. Next question is why are carbon dioxide removed in ammonia synthesis? Why are carbon dioxides or carbon monoxide removed in ammonia synthesis? So here the answer will be poisonous to ammonia synthesis, and the second is to produce more amount of hydrogen. So as already we know that carbon dioxide is detrimental or poisonous to the ammonia to the iron based catalyst used in the ammonia production. So that is why it should be removed. And the second one is if we remove carbon dioxides or carbon monoxide more, then the amount of hydrogen will be more, because in ammonia synthesis the reaction is what, N2 plus 3H2 produces NH3, right? So uh, 1 mole of nitrogen reacts with 3 mole of hydrogen. So amount of hydrogen is required more in this in ammonia synthesis process. So that is why if we remove more amount of carbon oxides, then it will get more amount of hydrogen, which will be favorable for the ammonia production. Okay. Next question is how does an integrated ammonia plant work? How does an integrated ammonia plant work? So you have to remember the flow chart here. So if you remember, you can write also. How does an integrated ammonia plant work? So first We are using natural gas. Okay. So we are using natural gas for the hydrogen production. So natural gas means mostly CH4, right? So CH4 enters into the desulfurization box. Desulfurization reactor means desulfurization means removing sulfur. So CH4 has impurities, small amount of sulfur is present there. So we first need to remove the sulfur. Okay, otherwise the reaction will not happen, will not get hydrogen purely. So first step is the desulfurization. Then comes the reforming. Then comes the reforming. In reformer, there are two type of reformer: primary reformer and secondary reformer. Okay, in primary reformer, there are two parts, that is combustion zone and then the reformed zone. Okay, so in the combustion zone CH4, in the combustion zone CH4 partially reacted with oxygen produces carbon monoxide and 3 moles of hydrogen, sorry, 2 moles of hydrogen, 2 moles of hydrogen, or methane can be fully oxidized to produce carbon dioxide and 2 mole of hydrogen. That is happening in the combustion zone. Okay, in the next slide I am showing. So in the reforming zone, what I have said, in the reforming zone, methane can react with water or steam. So here in the reforming zone, methane again reacts with hot steam, that is water only, and it produces carbon monoxide and 3 mole of hydrogen. Again it can react with the previously produced carbon dioxide to produce syngas, that is the mixture of carbon monoxide and hydrogen. So this is the reforming reaction happening in the primary and secondary reactor, right? Then after the, so here we have seen that first is a desulfurization section for removing sulfur, then comes a reforming section to produce hydrogen, then comes the, so after reforming section comes the water gas shift section. Water gas shift section means this carbon monoxide is converted into carbon dioxide. Okay, so almost all the carbon monoxide converts to the carbon dioxide. Okay, then CO2 removal because then only we can remove the CO2 by the methanation process, right? So the reaction of methanation process is CO2 reacting with hydrogen produced water and CH4, right? Yes, methane and hydrogen. You will see the stoichiometric balance. I am not correcting it. I am just saying that in the this is the equation of methanation reaction. Okay, so first CO is converted to CO2 in the water gas shift reactions, then CO2 reacted with hydrogen produces methane, that is called the methanation reaction. uh, that is called the methanation reaction, and then after the methanation what happens, that is condensation happens. Extra gases are purged out, and we are getting here extra gases are purged out, we are getting here like here ammonia synthesis is happening, from where we are getting liquid ammonia. Okay, like here it is reacted with nitrogen, and hydrogen is already present, so it is creating the liquid ammonia, and then this liquid ammonia is recovered. Okay, so this is the whole process of ammonia plant production, so you should remember it. So first the desulfurization, this is very easy to remember. So first you remember natural gas is coming in the desulfurization section to remove the impurities, that is mainly sulfur. Then it goes into the reforming section where there are primary and secondary reactors reformers are there, where in the combustion zone natural gas is reacted with oxygen to produce carbon monoxide, carbon dioxide and hydrogen. In the reformed zone, natural gas is reacted with steam to produce carbon monoxide and hydrogen, more amount of carbon monoxide and hydrogen. These carbon monoxides are detrimental to the catalyst. We have already studied that. uh, the catalyst is used an iron based catalyst for the ammonia synthesis, so that is why we need to remove this CO. So CO can be removed by, first it is converted to CO2 by the water gas shift reaction, then CO2 is removed by reacting with hydrogen to produce by producing methane. That is, the process is called the methanation process. Then this is condensed, this mixture is condensed, extra gases are sparged out, and whatever hydrogen is left here, that reacts with nitrogen and produces the liquid ammonia, and then liquid ammonia is recovered. Okay, so this is the whole process of integrated ammonia plant. Next question is the, in primary reformer of ammonia synthesis, dry gas mostly contains methane. Is it true or false? In primary reformer of ammonia synthesis, dry gas mostly contains methane, because mostly we know natural gas is used for the ammonia synthesis, so natural gas means mostly methane. Okay, next question is the, what is the temperature of the feed when it enters into the secondary reformer? What is the temperature of the feed when it enters into the secondary reformer? So when the feed enters into the secondary reformer, the temperature is very high. So it is around 1000 Kelvin. The answer will be 1000 Kelvin. Next question is, water gas shift reaction needs to be carried out at high temperature. Water gas shift reaction needs to be carried out at high temperature. Is it true or false? So here the answer will be false. Water gas shift reaction needs to be carried out in the low temperature. Okay, so why I am saying this? I am showing you the graph. So this is the water gas shift reaction temperature versus production curve. So you can see that at low temperature production is high, conversion is high, right? So that is why water gas shift reaction needs to be carried out at high temperature is false. Next question is what type of catalyst is used in the water gas shift low temperature reaction? So water gas shift reaction happens in two phases. Firstly, it happens in high temperature region, then it happens, then the product is being cooled, and then it happens in the low temperature region. So for the low temperature reaction, which catalyst is used? So here the answer is not iron based, okay, because high temperature reaction uses iron based catalyst, but low temperature water gas reaction uses copper based catalyst. So here the answer will be copper based. Methanation reaction occurs at 320 Kelvin. Is it true or false? Methanation reaction occurs at 320 Kelvin. Is it true or false? So it is true. You have to remember the chart from here. So all the stages reaction temperatures are mentioned. Secondary reformer needs 1200 Kelvin. High temperature water gas needs 700. Then lower temperature needs 500, and methanation needs 320 Kelvin. Okay, so here the answer is true. Next is the what is the temperature of ammonia synthesis process? What is the temperature of ammonia synthesis process? What is the temperature of ammonia synthesis process? So the temperature is 293 Kelvin. Okay. The temperature of ammonia is 293 Kelvin. 293 Kelvin means only 20 degrees centigrade. Okay. Next question is what is the composition of the purge? What is the composition of the purge that is coming out after the ammonia synthesis process? What is the composition of the purge? So here the answer will be methane, inert gas. Okay, methane and inert gas. Maybe a small amount of hydrogen will be there in the purge, but mostly in the purge gas after production of liquid ammonia, only methane and inert gas is left. Okay. Next question is what is the catalyst volume required in the desulfurization section? What is the catalyst volume required in the desulfurization section? So here the answer will be 76 meter cube. So it is given in the chart. So desulfurization case, the volume will be catalyst volume will be 76 meter cube. Okay. Next question is what is the correct order of the catalyst requirement in ammonia synthesis? What is the correct order of the catalyst requirement in ammonia synthesis? So this answer will also be from that chart what I have just shown. So you should be able to tell it. What is the correct order of the catalyst requirement in ammonia synthesis? So the I have not mentioned the correct order here. So this is the least. So if from here you have to mention the correct order. So let's go back to the chart first. So here you can see most amount of catalyst is required for ammonia synthesis and low temperature water gas shift reaction. Okay, that is 92 meter cube. Then comes high temperature gas water gas shift 86 meter cube. Then comes so we'll mark it accordingly. So this is the first. Okay, this is the first. Then this is also first highest order requirement of catalyst, that is 92 meter cube. Okay, then comes this high temperature water gas shift, that is, so this is 92, this is 8 this is 86, this is 92. Then comes the desulfurization, right? So it is in the third position, so it needed 76 meter cube. What was there after that? After 76, that is, there is 50, that is the secondary reforming 50 meter cube. Then comes the methanation process 38 meter cube. Then comes the primary reforming process, that is just 25 meter cube of catalyst are needed. Okay, so go back to the chart and mark it. So now secondary reforming, that is 50. Then comes the methanation, that is 36. Then last comes the primary reforming, that is just 25 meter cube of catalyst. Okay, so this is the order. Next question is what is the specific energy requirement for ammonia production in classical Haber-Bosch process? What is the specific energy requirement for ammonia production in classical Haber-Bosch process? So the answer is 80 to 90 gigajoule per ton. Okay, you see the chart and you will get everything. The classical Haber-Bosch process for ammonia synthesis is required 80 to 90 gigajoule per ton of energy, specific energy. Next question is what are the methods of hydrogen gas recovery? What are the methods of hydrogen gas recovery? So there are four steps of hydrogen gas recovery. Okay, cryogenic distillation. That means it happens in the cryogenic means it happens in very low temperature. So cryogenic distillation, adsorption, and membrane separation. Next is what is the purity of hydrogen after recovering by absorption? What is the purity of hydrogen after recovering by absorption? So what do we need to recover hydrogen? Because after the ammonia synthesis process, some amount of hydrogen is still left, right? So this hydrogen can be again used for the hydro treating of the natural gas, right? So that is why we need to recover this hydrogen. So by absorption, if we recover, what is the purity of this hydrogen, that is asked. So here the answer will be 85%. Okay, the answer is 85%. Next question is cryogenic distillation is a preferred technology for hydrogen recovery. Cryogenic distillation is the preferred technology for hydrogen recovery. Is it true or false? Cryogenic distillation is the preferred technology for hydrogen recovery. So the answer is not true. The answer is false because preferred technologies for hydrogen recovery are adsorption and membrane separation. So you can see this here. So this is the adsorption and membrane separations are the preferred technologies for the recovery Because cryogenic, as I have told already, cryogenic distillation requires very low temperature, that is 120 Kelvin, right? So it is in the minus degree, something degree centigrade, and absorption method does not provide the required purity. Okay, so it is lesser purity we can get in absorption. Okay, that is why preferred technologies are adsorption and membrane separation. So here the answer is false. Next is what are the two ways to do adsorption for hydrogen recovery? What are the two ways to do adsorption for hydrogen recovery? The answer is temperature swing adsorption and pressure swing adsorption. Temperature swing adsorption means TSA, where temperature is controlled, and pressure swing adsorption in pressure is reduced, PSA. It is PSA. Okay, in temperature, TSA temperature is raised, and in PSA pressure is reduced. Next question is which of the following property PSA does not depend upon? Which of the following property PSA does not depend upon? So PSA does not depend upon component? No. Partial pressure? No. Okay, it is volume of the gas. So PSA depends upon component, partial pressure and temperature. Okay, that is why these are the wrong answer here, because I have asked on which of the following property PSA does not depend. Okay, so this is the answer will be volume of the gas. Next question is thermal regeneration is carried out at 40 bar. Thermal regeneration is carried out at 40 bar. So thermal generation is not carried out at the 40 bar, because 40 bar means the high pressure. So thermal regeneration is carried out in low pressure, that is around 1 bar. Okay, in high pressure adsorption is carried out. Next is what is the correct order of recovery in PSA? What is the correct order of recovery in PSA? It is adsorption, depressurization and repressurization. Okay, after adsorption pressure will be high, that is why depressurization is needed, and again we need to do the repressurization to balance it. Okay, so recovery through hydrogen recovery through PSA follows this, not this, not adsorption, repressurization, depressurization. Okay, it is wrong. Next is the membrane separation based hydrogen recovery provides high selectivity. Membrane separation based hydrogen recovery provides high selectivity and high permeability of membrane. So you know that membrane, for membrane separation, membrane quality should be good. So that is why it is true, because it provides high selectivity and high permeability. Next question is what is the organic source of urea? What is the organic source of urea? So in 1828, German scientist Friedrich Wöhler synthesized urea first time from an organic compound that is named as cyanic acid and from an inorganic compound that is ammonia. Okay, so here I have asked for the organic source, so the answer will be cyanic acid. Okay, next is the which catalyst is used for urea production? Which catalyst is used for the urea production? So here the answer will be none of the above, because you know that in urea production any kind of catalyst is not used. Okay, so it is will be the none of the above. Next is the what is the pressure required in the first step of urea production? What is the pressure required in the first step of urea production? That is, the first step of urea production means when ammonia is reacted with carbon dioxide and produces carbamate. So in that reaction, so you know that NH3 in first step NH3 reacts with carbon dioxide, produces carbamate. So carbamate structure is NH2COO, and here there is NH4. Okay, so this is the carbamate. So in this reaction, the pressure is maintained at 130 bar. Okay, the pressure is maintained at 130 bar. Next, the carbamate to urea formation is much faster than the carbamate formation. So the second step of the urea production is H2NCOONH4. This carbamate decomposes to produce urea, that is urea and water. Okay, so this reaction is, we know that this reaction is slow, whereas this reaction was fast. So what I have asked the carbamate to urea formation is much faster than the carbamate formation. So here it will be false because it is slow. The answer will be false. Next question is what is the ratio of ammonia to carbon dioxide for maximum yield in urea? What is the ratio of ammonia to carbon? Okay, it is 3 to 5 mole per mole. Okay, so the answer is 3 to 5. Okay, if it is more than 5, then urea cannot form. Again, that is a problem. So you have to manage the ratio between 3 to 5 mole per mole. Okay. Next question is water concentration should be minimum in urea solution. This is true. So water is an impurity in urea production case. So that is why water concentration should be minimum. Next question is what is the pressure for carbamate decomposition? What is the pressure for carbamate decomposition? So we have seen that in carbamate formation, the pressure was 130 bar, right? But in case of carbamate decomposition, the pressure is low, that is only 20 bar. Then only carbamate can be decomposed to form urea. Okay. Next question is stripping process occurs at lower ammonia to carbon dioxide ratio. Stripping process occurs at lower ammonia to carbon dioxide ratio. Is it true or false? So it is true because in this case NH3 to CO2 NH3 to CO2 ratio is maintained at 3 to 3.7 mole per mole. Okay, so that is lower. Next is the which type of heat exchanger is used in the stripper of the semi-carbon urea process? Which type of heat exchanger is used in the stripper of the semi-carbon urea process? So answer will be falling film type shell and tube heat exchanger. The answer will be falling film type shell and tube heat exchanger. Let's see where it is in the lecture. So here, so this is the case of urea semi-carbon CO2 stripping process, urea production, and this is the heat exchanger. Liquid is like that falling film, and you know, and it is written that a stripper in the semi-carbon urea process is a falling film type shell and tube heat exchanger. So the answer will be this. Next question is the pool reactor provides longer residence time of liquid phase. It is not pole, it is pool reactor. My mistake. Pool reactor provides longer residence time of liquid phase. So it is true. Okay. So you will get this in the solution in the slides only, that this is a pool reactor, right? This is the pool reactor. So pool reactor provides longer residence time of liquid phase. Okay, so this is true. Next is the what is the reaction of burette formation? What is the reaction of burette formation? So the answer will be, so we formed carbamate, right? So carbamate is this. It decomposes and produces urea, but in when the temperature is high maintained in the reactor, it doesn't form urea. Okay, it forms plus ammonia. So this is burette. Okay, so why burette is formed? Because increased temperature is maintained in the in the urea synthesis process, and that accelerates the decomposition of urea to burette. Okay, I have done a mistake here because it is not carbamate. Sorry. Okay, so let me rewrite it. So the urea, after production of urea, that is H2NCONH2 decomposes to burette. H2L CONH2 plus NH3. Okay, so here the molecule of stoichiometry ratio of two molecule of urea. Okay, two molecule of urea will be decomposed to, this is burette, and this is NH3. So after production of urea, higher temperature is maintained in the, suppose higher temperature is there in the reactor, temperature is high, so then it decomposes to burette. Okay, so this is not expected. Okay, this is the disadvantage of keeping high temperature, so we have to avoid the high temperature. But again, burette formation is follows this reaction. Next question is the next and last question is that to reduce the corrosion of ammonium carbamate, oxygen is added. Is it true or false? So there are a number of steps followed to reduce the corrosion. Okay, so some measures to limit the corrosion of the construction materials, that are construction materials can be stainless steel so that there will be no corrosion. Again, addition of oxygen with the feed so that metallic oxide layer protect from corrosion. Okay, so to reduce the corrosion of ammonium carbamate, oxygen is added so that oxygen is added with the feed so that metallic oxide layer protect, so that on the construction materials of the reactor, a layer of metallic oxide is formed and that will protect it from corrosion. Okay, so this is true. Okay, so this is from my side. I hope you will find these questions helpful for doing the upcoming assignment for uh, assignment 4. I hope you will learn from this, and if you have some query you can ask in the discussion forum. And till then, good evening. uh, till then, goodbye. So okay, I am ending it.